Hello everyone. Today we will see that when potential energy is given as a function of x, then how time period depends on energy and amplitude. For a dynamical system, you know that the total energy is sum of the kinetic energy and potential energy. Now total energy E is equal to 1 by 2 mv square plus Vx. Here V is velocity and you can write it as dx over dt. V is here potential energy. Let us say this is equation number 1 and this is equation number 2. Now we can write E as 1 by 2 m dx over dt whole square plus Vx. So it is equation number 3. Now we will find the value of dx over dt by equation number 3rd. Then we see that dx over dt comes out to be root 2 upon m e minus vx. It is equation number 4. Now we can find the value of dt and it comes out to be root m by 2 dx upon root e minus vx. Let us say it is equation number 5. Now we will find the value of t. How we can find the value of t? We will integrate the equation number 5 and then it comes out to be t equal to root m by 2 e to the power minus 1 by 2 dx upon root 1 minus v upon e. Here e is the total constant, so we can take it out. And now we can write your time is equal to root m by 2 e to the power minus 1 by 2 dx upon root 1 minus v upon e within the integral. It is a very important relation and you have to remember it. It will be used in further applications. Now we will check that how the time period depends on energy and amplitudes. First we will find that how time depends on energy. Okay, so let us put v upon e is equal to y. It will be a variable and dimensionless because v is potential energy and e is energy, so it will be a variable but dimensionless. Both v and e have same dimension. Now we will take the first case. Here your potential energy is equal to beta x to the power 4 and it is a known simple harmonic case. Beta is here a constant, so when we put the value of v beta x to the power 4, then your t comes out to be root m by 2 e to the power minus 1 by 2 integration dx upon root 1 minus beta x to the power 4 upon e. Now let us put beta x to the power 4 upon e is equal to y. I already defined it that it is a dimensionless variable. So we will find the value of x, that comes out to be here ey upon beta to the power 1 by 4, or we can write it as more is easily formed e to the power 1 by 4 y to the power 1 by 4 beta to the power 1 by 4. When we put this value, then your time period comes out to be proportional to e to the power minus 1 by 4, because this whole term looks like a constant and the integration of 1 with respect to d1 with respect to x, it comes out to be x. So when we put the value of x, then your whole expression comes out to be that t is proportional to e to the power minus 1 by 4. So here you see that your time period depends upon the energy and it is proportional to e to the power minus 1 by 4. So it is a very important relation and you have to remember it. Now the second case, that when your potential energy is equal to 1 by 2 kx square, where k is a constant, it is force constant you can say, Now this is the case for the simple harmonic motion. For simple harmonic motion, you know that your restoring force is proportional to x, or you can write F is equal to minus kx. You know that when potential energy is function of position, then you write your force is equal to minus dV over dx. So dV comes out to be minus F dx, and when you integrate it and find the value of V, then it comes out to be 1 by 2 kx square. Here k is a force constant. So we will again put V upon E is equal to Y. So V is equal to 1 by 2 kx square upon EY. Then x comes out to be like this value. When we put this value in earlier relation which we have find for time period, then it comes out to be that t is proportional to e to the power 0. Here you see that time does not depend upon energy in case of the simple harmonic motion, so it is also a very important relation and you have to remember it. We will consider the case for the amplitude. You know that amplitude is defined as the maximum displacement, and at maximum displacement your V is 0. So when we write the formula for total energy, you know it is kinetic energy plus potential energy, and you can write it as E is equal to 1 by 2 mv square plus Vx. Here it is potential energy and V is here velocity. You should not be confused in these two terms. So at maximum displacement, x equal to a and V is equal to 0. So when we put V equal to 0, then your this term is 0. So E comes out to be Vx. When we put x equal to a, then it becomes E equal to Va, right? When we first case, when we consider V is equal to beta x to the power 4, then you see that your energy comes out to be proportional to a to the power 4. And when your Vx is equal to beta x square, then E is proportional to a square. So in non-simple harmonic case, energy is proportional to a to the power 4. Here a is amplitude, and for simple harmonic case, your energy is proportional to square of the amplitude. Again, these two are very important relation, and you have to remember this, right? This is non-simple harmonic case. I will also write this. Now we can find the relation for time period also in terms of the amplitude. You know that your V is equal to beta x to the power 4 for non-simple harmonic case, and we have already derived the time period is directly proportional to e to the power minus 1 by 4. So if we put the value of energy in terms of the amplitude, then you see that your time period comes out to be proportional to 1 upon a, or in case of non-simple harmonic case, the time period depends upon the amplitude, and in case of the simple harmonic motion, time period does not depend upon the amplitude. Thank you.